Hello students, this is lecture 17 of MTH 201. In the last lecture, we discussed Lagrange multiplier method and various versions of it. So let us recall the definition of a curve, path, velocity vector and tangent line. So let I be an interval in R which can be of any type. It could be all of R, it could be an open interval AB, closed interval AB, or something else. A path in the plane R2 is a function C from interval I to R2, and a path in space is a function C from I to R3. The image of the path C is given by the values Ct or the point Ct, where t varies over the interval I. So that's the image of this path, and it's called a curve. And the path C is called parametrization of this curve. Also, the path C is said to parameterize this curve. So we have seen examples where a curve can have two parameterizations, right? The point Ct is called the position of the particle at time t if we think of it as motion of a particle. And the velocity of the path c at time t is a vector which is defined as c prime t is limit h goes to 0, c of t plus h minus ct divided by h provided this limit exists. And how do we draw this velocity vector? Remember, this is a vector because c is giving you a vector, right? So this is a vector, and velocity vector is drawn with its tail at the point Ct. So you are on the curve at the point Ct, and then you draw the vector c prime t, which is the velocity of this path at time t. The speed of the path c at time t is nothing but the magnitude of the velocity vector, which is norm of c prime t, or the length of c prime t, which is the length of the velocity vector. And what is the tangent line at the point ct naught for a particular t naught in the interval? It's given by ct naught plus t minus t naught c prime t, which is the direction. So you are on the walking along the velocity vector. Okay. So this is something that you already know. Now let us take inspiration from this and let us define in general what are called vector valued functions. So a vector valued function is a function whose domain is a subset of the real line. Okay, so it starts from a subset of R and whose range is contained in Rn for some n. And in this course, we are going to focus on n equal to 2 and 3. So we are going to look at functions whose domain is a subset of R and which go to either R2 or R3. So we are going to look at vector valued functions whose image is either in R2 or R3. So suppose the vector valued function takes a point in R2, a point in R3, then R at t is a point in R, it will have three components, right? Because it is going into R3. So these ft, gt and ht. So we can also be written as fti plus gtj plus htk. So I am not placing triangular brackets here. I am just putting it like this to signify it as a point in R3. And where fg and h are all functions from R to R, right? Because these are just the components, right? So they are real numbers for every real number t. What is the graph of RT? It's the collection of all terminal points ft, gt, ht for all possible values of t. So you look at all these vectors. What is their terminal point? The terminal points are ft, gt, ht, and you look at the collection of all such points. for every value of t which is possible. Now the variable t is often referred to as time variable, and rt is often referred to as position at time t. We'll come to this issue again, okay, in some time. Now a path, as we have defined earlier, it's a vector valued function, right? Because the path goes from an interval which is sitting inside R to either R2 or R3. So therefore a path is a vector valued function. We can define operations on vector valued functions. The first operation we can define is called addition. So if you have two vector valued functions, let's say on R3, which are R1t and R2t with components f1, g1, h1 and f2, g2, h2, then you can add these vector values excuse me, and evaluate at the point t. It's nothing but R1t plus R2t, and then you have just vector addition, right? Which is component wise addition. Then the other operation you can have on functions is vector valued functions is scalar multiplication, where you multiply a vector valued function with a scalar c, and what you get is component wise multiplication. So you multiply that scalar c with each component. Okay. And if your vector valued function is going to R2, then in all these steps you just drop the third component, right? Because you just have the I component and the j component. So this is pretty simple. This is very similar formulation as we did for paths, right? Let us look at a few examples. So let a, b, c be real numbers, and consider this rt as x0 plus ta, comma y0 plus tb, comma z0 plus tc. So if you think carefully, this can be written as x0, comma y0, comma z0 plus t times a, comma b, comma c, and that's the equation of a straight line. Then rt is a vector valued function on R3. The graph of R is a straight line in R3 which passes through the point x0, y0, z0, right, when t equal to 0, and its direction vector is ABC, right, t times ABC. So that's the direction. The same example we also looked at when we were studying paths and curves. Now let a and b be positive numbers and consider this function rt, which is a cos t, comma b sin t. It's again a vector valued function on R2, right? Now the image is in R2. And what is the graph of R? It's an ellipse in R2. How? So if I divide the first component by A and square it, you get cos square t. Take the second component and divide by B and take the square, that's sin square t. What is their sum? It's 1. So the equation that you get on the xy plane now, where the image is lying, is x square by a square plus y square by b square equal to 1, right? That's an equation of an ellipse. And when a is equal to b, you get a circle of radius a, right? This is another example. Now let us look at this third example again of a vector valued function on R2. Here rt is equal to t comma t cube, okay, and it's again a vector valued function on R2, and what is the graph of R? It's nothing but the curve y equal to x cube. How? Because if you look at the y component, which is t cube, that's nothing but the cube of the x component, which is t, right? So the graph is nothing but the curve y equal to x cube. All right. Now let us define operations, calculus on vector valued functions. So let Rt be a vector valued function on R3 with components f, g and t, f, g and h. The limit t goes to t naught, Rt is defined as, you just put this limit to each component, right? And each component is a function from R to R. So you know what the concept of limit is there, right? So in what case do you say this limit exists? When all these three limits on the right exist. Then you say that this limit t goes to t naught rt exists. And otherwise, even if one of these limits does not exist, we say that the limit t goes to t naught rt does not exist. Okay, so rt limit will exist if and only if all the three limits exist. That's the definition. When do we say that Rt is continuous at a point T naught? If this limit exists and it's equal to Rt naught. What is Rt naught? Rt naught by definition is Ft naught, comma Gt naught, comma Ht naught. So when are two vectors equal? When they are equal component wise. That means all we are asking for is that Rt is continuous at T naught if and only if F, G and H are all continuous at T naught, right? That's the definition. Now, how do you define derivative of RT? It's defined as R prime T naught is limit H goes to 0, R of T naught plus H minus RT naught by H. Remember, this is now a vector, right? Because R in the numerator you have a vector, difference of two vectors. So when this limit exists, you say that derivative exists and it is defined as r prime t or dr by dt. And again, the second derivative is defined as the derivative of the first derivative if it's defined and so on. And if the derivative exists, then what is r prime t naught? It's nothing but component wise you take the derivative. So that means, this is a crucial point about vector valued functions, that whatever properties from calculus, which is limit, continuity or differentiability we are talking about, it's equivalent to each component having that property. So if we are talking about existence of limit of R, then all these three components should have the existence of limit. If we talk about continuity, then all three should be continuity. If we talk about differentiability, all three should be differentiable. Okay, so it's something that is dependent on its component function. So the component functions properties completely describe the properties of R. So the properties of a vector valued function is determined by the properties of its component functions. Let us look at this example. So consider Rt to be t, 5t plus 1 by t square. So now the third component does not have a limit when t goes to 0, right? So this limit does not exist, we know that. Therefore, Rt cannot have a valid limit when t goes to 0, right? Because one of its components, even though first and second component, the limit exists when t goes to 0, but because the third component, for the third component limit does not exist, Rt does not have a limit at that point. However, if you take any other t naught which is not 0, then the limit exists, and what does it equal to? It equals to component wise limit, right? So if t goes to t naught, limit of t is t naught, 5t plus 1, it's 5t naught plus 1, and 1 by t square, it's 1 by t naught square. So that is the limit when t naught is non-zero. So therefore, putting all these things together, and also remember this is nothing but RT naught, right, by definition. So therefore, RT is continuous at all points t where it is defined. Now, if you look at this function R, it's not defined at t equal to 0, right? So at on its domain, what is its domain? When t is non-zero, so on its domain, RT is continuous at all the points, right? But it cannot be extended to all of R, meaning you cannot find a continuous function on all of R such that it's equal to R on points which are non-zero. Okay? And when T naught is non-zero, we can easily compute that R prime T naught is given by 1, comma 5, comma minus 2 by T naught cube. Again, this makes sense when T naught is non-zero. So T naught, because it's not even in the domain of R, we don't really talk about it, but we can still talk about limits, right? Okay. Now let us define this useful concept of unit tangent vector. We have already defined tangent vector, right? For a vector valued function r, its tangent vector is nothing but r prime. Okay. Just like when we talk about paths, right? So in the figure, C represents the graph of a vector valued function Rt in R3. So you can see that this black solid curve is the graph of the vector valued function Rt. Now let P be equal to the value, the point position vector Rt, and Q be the position vector Rt plus S, H. Then the blue vector, which is this vector joining PQ, is a scalar multiple of RT plus H minus RT, right? Because that is the direction of this vector. And assume that R prime T is non-zero. So this is an important assumption that we make all the time to make these things work. So R prime T is non-zero. So it's a non-zero vector, and you can see that this vector is like this, right? It's tangent to the curve at the point RT. Now you consider the vector RT plus H minus RT divided by H, right? That's a vector in the direction of this blue vector, isn't it? Because the direction of blue vector is nothing but RT plus H minus RT. Now, as H goes to 0, as the distance between P and Q goes to 0, so see, now I moved from H going to 0 to distance between P and Q goes to 0. Why does that happen? Because if H goes to 0, then RT plus H goes to RT, right? Because this T plus H goes to T. So as H goes to 0, if you look at this vector RT plus H minus RT by H, that converges to the velocity vector R prime T, right? That's what we learned from the definition of R prime T. And this lies on the tangent line to C, right? So if you look at the tangent line to C at this point, this is what it is, right? So I'm sorry, there's a spillover on this slide, so I can tell you what the unit tangent vector is. I would request you to go to the PDF file to look at the actual definition of unit tangent vector. It's nothing but r prime t divided by norm of r prime t, the length of r prime t. So it's nothing but the tangent vector and the unit vector in that direction, right? How do you make a vector unit? By dividing by its length. So that's the definition of unit tangent vector. I'm sorry about this. There is another line here in this slide, as you will see in the PDF. Okay. Now let us look at few properties of derivatives. So let us look at two functions, vector valued functions r1 and r2, whose components are f1 g1 h1 and f2 g2 h2. And suppose a and b are two functions from R to R. So they are real valued functions. Then there is a sum rule which tells you, I'm sorry, there should be a plus sign here. If you take derivative with respect to t of sum of two vector valued functions, that's nothing but the sum of their individual derivatives. Scalar multiplication, if you multiply a vector valued function by a scalar valued function and you take derivative, you have like product rule, as you have seen in one variable. But now these are vectors, right? Both of them are vectors. Dot product rule, if you take dot product of two vector valued functions at the point t, take the derivative, again you have like a product. Okay, but you have dot products here, right? Cross product rule, again, if you take cross product of two vector valued functions at the point t, differentiate, then you have like a product rule. Then you have chain rule, where if you apply at, which is in R to R1, which is a vector valued function, and you take the derivative, it's nothing but a prime t, which is the derivative of the inside, times derivative of the outside, which is r prime, r1 prime at at. Okay, so these are several properties, and we will be discussing these in the tutorial. Okay, so I will not discuss those here. Now, let us relate all of these. We were using terms like time, position, velocity, speed. They very much look like terms that we see in for that we use for motion of a particle, right? So consider motion of a particle in space described by a vector valued function where the component functions have continuous second order partial derivatives. So this is important condition here. We are taking continuous second order partial derivatives. Okay. So you can imagine this as follows. So at time t, this vector or this thing that you see on the right hand side is a point in R3, right? So this function, this vector valued function is actually telling you that at time t where you are, okay? So this RT, which is FTGT HT, is known as the position of the particle at time t. Its derivative is known as the velocity vector. So what is the velocity of the particle at time t? And the magnitude of the velocity vector is called speed. So what is the speed of the particle at time t? And if you take the second derivative of r, then that is known as the acceleration vector. Okay, and it is nothing but the second derivatives everywhere. Okay, so let me just go back to the slide. So that's how I'm relating now vector valued functions on R3 with motion, understanding motion of a particle, right? And we now have a relationship between the old terminology of position vector, velocity vector, speed that we used with this. And this is something that you know from physics, right? Okay. Now we have talked about limits, continuity, differentiability. Now let us come to integrals. So suppose you have a vector valued function on R3 with components f, g, h. You define integral from a to b rt dt as you now push the integrals to each component, and provided all these integrals exist. Now you know the notion of Riemann integrability. So that's the integrability, that's the notion of integration that I'm talking about here. So if all these three limits exist, all these three integrals exist, then we say that the function rt, vector value function rt, is integrable. Otherwise we say that it does not exist. Now since this is defined in terms of integrals of its component functions, whatever properties you had for integrals for functions from R to R, all those properties will transport to this vector value function, right? So this is a similar note that I made while defining continuity, differentiability and limits, that whatever properties does the component function have, the same properties are inherited by the vector value function. So this is where we stop, and we'll continue our discussion on vector valued functions in the next lecture as well.